Hello, everyone. Thank you for joining us today for another whiteboarding session. Today we have Chase Smith and Alex Rosnick from Proxima joining us with Bowen from Near Protocol. Take it away, guys.
Yeah, so I'm Chase. I'm from Proxima. I'm co-founder. Alex is another co-founder of Proxima. Basically, Proxima is designing a scalable data layer to provide fast and efficient reads for indexed DApp data. And we do this while maintaining the security of the blockchain that the DApp is actually located in. So if you're using a DApp on Ethereum, you would want the same security as you have on Ethereum. You wouldn't want to be using a secondary consensus layer. So before we get into Proxima, I'd just kind of like to talk about the blockchain data layer. There's been a lot of discussions on the blockchain data layer, and what you have for the blockchain data layer, for every blockchain that's smart contract based, right? You have to have some form of state associated with it. But for every blockchain, each block has some, block hash, and along with that, it has some state root that is associated with a Merkleized index of the data. So in Ethereum, it's the Patricia Merkle tree. In Cosmos, it's going to be the IAVL tree. And, you have a variety of different Merkleized index structures. One of the key issues that happens for the blockchain state, one of the key issues that a lot of projects are facing is that the state is not just this, right? The state is actually a set of diffs, right? This is a version state. So you have a set of diffs and you have a state root associated with each separate block. This means that you're going to be increasing the state, the total state of the blockchain in relation to the number of diffs. And we can say, okay, that's actually just going to be related to the number of changes or updates. So it's going to be equal to the number of transactions, right? Each transaction, you're assuming there's going to be an update to the data state. And since each of these diffs requires some log n Merkle index, right? Some branch of the Merkle tree to handle, it means that the size is going to increase, consistent with the number of transactions. And so there's a lot of solutions to this problem. A lot of people will go specifically for the blockchain route. Let me just check out if I can erase this. A lot of people will go specifically try to optimize the full nodes or the blockchain nodes. And what this means is they'll try to compress the snapshots so that they don't have as many diffs. So maybe you store every 1,000 snapshots. Or you have guys like TurboGeth where they will store an optimized version, right? So TurboGeth stores the Merkle state in a balanced tree. It has optimized database queries. It has optimized accesses, right? Because you don't have to access you don't have to go through as many levels to iterate through the actual Merkle index.
Sorry to interrupt. So like when you talk about it increases proportional to the number of transactions, I assume you're talking about the case where you need to maintain the entire history of states because a transaction doesn't necessarily create a new...
So I was giving you the solution of blockchain where blockchain is a version state with each block representing some update to that state. And so you have to store the diffs because the traditional way that the blockchain works, right, is that, sorry for the drawing, is that the nodes for the blockchain don't actually, like say this is here, right? You have a full tree for the blockchain, but actually portions of this tree are going to tie back in to other snapshots, right? So if this branch doesn't update, you're going to have to store this. So you can prune these unneeded branches if you want, and you can compress them, and that's one of the solutions. But at this current state, right, we're assuming that the blockchain has a version for every block. So what something like TurboGet does and Cosmos do is they try to, they say, okay, well, we don't need to store every single snapshot. We can store every 1,000 snapshots. And that's actually, it's a solution. It's a solution for the full node to achieve optimized write consensus. So, you can write more effectively if you're not dealing with huge data sets. You can partition the nodes better if you're not dealing with huge data sets. You're still creating blockchain nodes, though. So it provides an effective write layer, but it doesn't provide as an effective of a read layer. So let's kind of look at the case of like a DApp. Right, you have some DApp on a blockchain, and this DApp state is represented by a set of smart contracts. The manner in which these smart contracts are distributed on the full state of a blockchain is not going to be indexed. Right, it's not going to be sorted. You might have a contract here, right? C1 is over here. Maybe you have another contract over here, C2, and no matter how optimized you get this state for writes, for inputting data, you're gonna have this issue where the data for DApps is not indexed for the DApp. So what that means is for a DApp to get its contract information, it has to make multiple random requests to the blockchain state. Does that make sense? I'm gonna take that as a yes. They have to make multiple requests to the blockchain state. And
I mean, it depends on what is drawn here, like, and what is the I guess what is the way you store the data for the DApp. I think that is more blockchain specific.
So if you use if you store the data off chain.
No. I mean, even on-chain storage, right? Like, it's yeah. I mean, it's not clear what is drawn here. Like, if you represent this as you're talking about some subtry, then sure, I agree with that.
Yeah. So if you have a DApp with one main contract, and it has a list or a mapping of multiple other contracts, say ERC20s, right? The hash for all of these contracts is going to be different, right? It's going to be randomized.
So you're talking about, okay.
So when you're trying to get data from multiple smart contracts, you're going to have to make these randomized requests where you're going from.
Okay, yeah, I think it was not clear that you were talking about the specific specific structure where you have interaction between a lot of different contracts.
Well, yeah, so if you only have one smart contract, you can get around a lot of the issues unless your request you'll have addresses associated with it, right? Because different accounts are going to have randomized hashes as well. So this has caused a significant concern for developers requesting data from the applications. It's not as much of an issue on the full node side. But I think it's one of the bigger issues, I would say, of concern is specifically the read layer, because there are significant difficulties right now with scaling the read layer. And while the write layer, you have some defined, you can only write, say, 1,000 transactions per second, 10,000 transactions per second. You have the defined threshold for that. You have a defined threshold on, say, okay, we know we're going to get 100,000 transactions per second. We know we have to write these to the data. What kind of performance optimizations do we need to do to ensure that we can store this data effectively for the blockchain? For the read layer, you need something different, right? So for the read layer, you want to look at how do we get this DApp to get its data effectively and fast. The optimal, the obvious case is something like Infura, where it's centralized. You get, you request data and you trust the the services of Infura.
Sorry, just to be clear, when we're talking about that, what it means for the dev to have fast access to data, do you mean that do you mean on the front end or on the smart contract side?
So on the front end, the read layer of data is going to be off-chain individuals who are seeking blockchain data. So it's, generally speaking, in database systems, you will see a significantly higher proportion of reads as opposed to writes. So that's the methodology is how do we offload as many of these writes from full nodes onto this read optimized data layer, and how do we ensure that this data layer can scale with usage, right? Not based on just attaining 100% availability for this data layer. The key to this is, or one of the keys to this is say, okay, we know this has these smart contracts, right? Contract 1, contract 2, contract 3, and you have some main smart contract. So you have a variety of index data throughout the blockchain DApp. We know it's going to be randomly distributed in the state for the blockchain, but what if we could find a way to only store this data, right? And to create an index for it, right? And, create a method to query it in a fast and useful way. So if you only store the DApp data, it's going to be a smaller storage. If you're storing it in something like a traditional database, though, you lose a lot of the security. So while you can optimize for the data, right? You can optimize for the query speed. You still need to be able to maintain that same level of the same level of security as the blockchain, or you need to maintain some level of security. So some solutions for this have been to say, okay, say you have the blockchain here. We know we want the DApp data in some, centralized database, some database that we have, a traditional database. All we need to do is create some sort of state transition to the database from the blockchain. And we can just tie this state transition. We can tie this data, any request from this data, to a consensus system. And every request will get the consensus. We'll have some form of consensus around the data. And if they want to, they can then audit the data to ensure that it came from the blockchain. This seems very easy, right? You can just implement the state transitions. You can store it in a traditional database. Consensus systems are pretty well fleshed out. You could use something like Tendermint if you wanted to. The only issue, right, is that instead of having this as your security layer, this becomes your security layer. So how do you ensure that you can get this in as consistent a method as possible, right? How do you ensure that this data is going to be consistent without compromising on the security? And for our method, we said, okay, let's just take this from blockchain. We already have a blockchain. We're already using that. We already have a consensus. So we don't actually need to use a consensus to prove that the data is correct. We already have these state transitions. What if we just stored this in some form of, authenticated database? And every query could just take a proof as well, right? Query, and you get some form of proof response, right? Data plus proof. And this would be an authenticated data store. So something that's, it could be a variety of different things. Generally speaking, a lot of these are Merkleized. And so that was the initial thought process. Instead of using consensus, you use an authenticated data store, maintaining that same type of state transition, but if you can optimize the authenticated data store, then you can start getting very, very interesting read queries. And so we decided to say, okay, well, let's focus on, where the data store and where the data structure needs to be updated and where it can do a lot better. Oh, 1 minute. So the traditional method for storing data is you have some tree structure in blockchain. Sorry, the traditional method for storing data in a blockchain is to have some form of Merkleized index, right? Like a Urkel tree. And for each one of these leaves, say #2, each one of these leaves, you're going to store this leaf. Let's say key, right, and value. For each one of the nodes in this data structure, in this Merkleized data structure, you're going to say, okay, this root hash is a key, and it ties to the value of, H1, of the value of the node itself. What this creates is a database that contains a randomized set of keys for each branch. The reason that they're randomized is because they're hashed. So for every operation in this data set, you have to iterate through a variety of database keys. So for instance, you want to get this key, you would have to request the root from the database. The database would then have to look that up through the disk. Then you would have to look up the hash, the second hash, the second layer. That would be another random read for the database. And you'd have to continue doing that until you got to the key and the value. So this isn't very effective because you're using database requests, right? You don't want to be using database requests for nodes. You want to be only using those for keys. And the whole thought process behind this, comes from, or the new thought on this comes from the guys at Handshake with the Urkel DB, where they said, okay, instead of using a database to store all the nodes, why don't we just use an index database structure, right? Why don't we use a Merkleized index as the database index? And if we do that, we can create the same type of structure as a flat file database. And this is what the flat file Urkel tree is. And the methodology for the flat file tree is you are storing the actual index of the Urkel structure as the index of the database. So instead of requesting database operations, you're requesting memory and storage operations. And I think this is one of the more valuable points, and the one that we should kind of go into is what's the difference between these two structures. So what is it really a big deal to request database to request these nodes from the database as opposed to just requesting them from data storage, a flat file system? And it's it's the equivalent of running a database on top of a database if you don't do it. And that's kind of the key fundamental portion of what we're doing. And I don't know if you guys have any questions on the Urkel tree, but it's similar to a database, right? You have some form of table that acts as the head, and this head has pointers to various other index tables for a variety of other branches, and then finally you have some value. And these are all pages in the file system. So it's important to note that each individual page is not equal to a node. You store these nodes, you store these pages as some subsection of the actual Merkle tree that you're using, right? And this includes the pointers to the relevant data, right? So the concept behind the flat file tree is to say, hey, listen, we're going to be using Merkle trees for a while. We're going to be using authenticated data structures for a while. They make sense. How can we update things so that we're not using traditional systems? We're using systems that are designed for this. And I don't know if you guys have any questions on that. I know you guys are interested in specifically flat file tries and the data structures involved in them. I think the concept is the flat file. The important concept to note here is the flat file versus building on top of a database. I think specifically with relation to data structures, it really depends on what you're trying to optimize. Specifically with indexing, you want to optimize data structures for rich queries. Whereas potentially with a write only, you might, the Urkel try might be good. I don't know what kind of struggles you guys, what kind of difficulties you're facing in the in your own writes, but I know that batching does work for a lot of write operations, but it does not scale very effectively because of the number of random memory hits that you're getting on the database.
Yeah, I think there are several questions here, right? So I saw one question from the chat. Is the flat file Merkle tree a strict improvement, or is it only improvement for read?
It's only what?
Improvement for read.
It's a strict improvement. So it's an update on how you're storing the actual database values. So what I was trying to say is that when you're storing your Merkle tree in a database, what you're actually storing is all of the hashes as well as the keys and values. And you're storing these in an unordered format because they're randomly hashed, right? So this could be 4, right? This could be, this could be 5, and this could be 8. Obviously that's, I'm just trying to make it simpler. This, it's gonna be a 32 hash, but yeah. So the issue with that is that when you're requesting this data, and when you're requesting this data, you have to make these database requests as well. And you have to make multiple database requests. And when the database gets this request, it's going to be traversing the same type of index that the flat file tree would be traversing. So instead of having, X number of indices, you have just one. Right. So instead of X number of database requests, you just have a single one. And that it scales very well, specifically with larger data sets where the Merkle tree or the current implementation of these Merkle structures does not. And the reason that the traditional Merkle structures don't is because of caching. So whenever you read one of these pages, it's going to cache the page. And so if you get a lot of random keys and values for a large data set, you can cache a lot of pages and they're not going to be relevant to your other searches because it's random. It's random data. It's random nodes.
I understand.
And yeah, so I would say that's a big difficulty. I think the batch writes really do help that because, you're not having to write these individually. Ooh, 1 minute. You're not having to write each one of these values individually. You can create a structure of the tree and then have those ordered and write those in order. So, instead of writing 10,000 values individually, you can write them in order. It still will present an issue eventually, but I think the bigger issue is when you're trying to create those batch of writes and you get a significant number of reads at the same time, the reads can mess with your cache. Right. So if I give you a ton of different reads, a ton of different random reads, even if I'm not trying to be malicious, you could be storing a ton of different pages in your cache, and none of them are relevant. So now you have to start going back to the disk each time. And that's where the real slowdown goes. So as long as you have memory, all of these blockchains say, hey, listen, we're doing awesome. We have all of this awesome stuff. We can handle everything in our cache. We can handle everything in our memory. We're not really hitting storage very often. And then when you hit that point where you are hitting storage, it gets really bad. And that's where you see the issue where someone's like, hey, there's a buffer overflow. All of my my node just crashed. I don't know why my node crashed. The issue is because these transactions are being delayed so much because of the hits to storage.
Yeah, can you talk maybe a bit more about how the flat file Merkle tree is indexed? Like how are they how is the tree divided into pages and so on?
Yeah, so it's similar. It's almost exactly the same as a traditional database system that has a copy on write. So if you look at a traditional tree, just a regular tree, right, it'll have a variety of branches that are pointing to one another. The way to transfer this into pages, generally speaking, they'll take some portion of this tree, say up to level 2, and they'll store it in a page. And the pointers here will then reference the other pages, right? So you'll have the node as well as, next node pointer. So that's how the system works. And this is going to be a pointer to a storage, a specific file with an offset. I would say that, so the storage of the specific storage of this, if you guys are looking into getting involved in, if you're looking into implementing some type of flat file trie, I would say the easiest thing is look at your writes and then determine the indexing structure that's going to optimize that. And you can likely use a traditional database pagination scheme. So these schemes are open, right? Like the point is these pages, this is not a new thing, right? The new thing is using a Merkleized index with as a database index. Like database indices have been done, right? People know how to do that. It's integrating the Merkleized index into it that is the unique aspect. And I think that's, the Handshake guys did really well. I think Urkel DB has a potential for very effective gets and puts. So I think it has a potential for the write layer. If you want to add it to the read layer, you are going to need a higher complexity of queries. So you're going to need to be able to do range queries as well. You're going to want to be able to store variable length keys, and you're eventually going to want to be able to go to a higher complexity of queries. And that's going to require a different data structure than what the Urkel DB is.
Okay, yeah, I'm not an expert in this area, but we do have some database experts here.
Yeah,
Alex and Misha, do you have questions here?
Alex? So one of the things that you guys, I know you guys use RocksDB, right? So one of the things that you could do is you could look at the index structure for RocksDB and say, okay, how do we turn this index structure into or how do we, change this index structure to a Merkleized index? Or, what else can we do? I don't know if it's going to be a huge issue now for blockchains with writes because of the ability to batch them. I think it's more of an issue for the read layer. So I think the optimizations are more of an issue for the read layer. I think also the read layer is going to be, it's going to be a different animal because the read layer, the one that we've designed, we don't take into account, the assumption is that you already have 100% data availability from the blockchain, right? So you can always recreate whatever database state you have.
Yeah, I mean, read layer, yeah, it's going to be a problem, but like that's, I feel like that to us is somewhat of a separate problem because it's almost like it's not a protocol level thing, right? Like on the protocol,
yes.
On the protocol level, what you're more concerned with is right, as you suggested, and of course for smart contracts. Definitely people want to build, extra indexing on top of it such that you can query the state in a very fast way. I mean, that's definitely very, very desirable. But I think our primary concern is, how we can optimize our tries so that on the protocol layer, it's more performant. And but I mean, the read layer you're talking about, yeah, definitely also very, very nice. But I still feel like we're going to maybe look at that separately from
yeah.
Yeah.
So this index and these indexing structures are they'll help both layers. The reason that I try to make a distinguish, the reason that I'm trying to distinguish between the read layer and the write layer is that the write layer has different assumptions that you need. You have to have different layer of availability for the write layer. So not only do you need consistency, you also need to have 100% availability for the information, right? To ensure
sure.
that the transactions are correct.
Sure,
With the read layer, the benefit is that you don't actually need that, right? So if you create a blockchain agnostic read layer that's designed specifically to index DApp data, here, let me. So you're assuming if you're creating this read layer that's specifically designed to index DApp data, and you have this DApp index, you don't actually need 100% availability because everything from this DApp index comes from the blockchain. So if you lose any data, someone tries to withhold any data, you just recalculate it. Yeah. So it's
this is more like designing a kind of separate service from.
It's a blockchain agnostic layer. Yeah. It's designed. It's designed to be made for blockchain. It's blockchain agnostic. I think the reason to focus on the read layers again is because if you don't focus on the read layers, if you don't try to offload as many reads as possible onto some other layer, it will get in the way of the write layer. And you're going to have two different approaches to the read and the write layer, right? If you're trying to do batching while you're in the write layer, while you're getting a ton of reads, it doesn't work. And I mean, traditional database systems, generally speaking, they'll have they'll write a set of events, and then they'll have those events transformed in some database. This is generally speaking how the traditional systems will work, right? You'll have some sort of event stream, and then you'll have some form of state transition, and that will get put into like a read-only database. And so this is just kind of taking that traditional approach and pushing it towards blockchain so that we don't have to, so that blockchains don't have to handle too many problems. Like they don't have to handle the read layer and the write layer.
Yeah, I mean, definitely makes sense. Yeah, can you maybe talk about some of the results that you obtained? Like, what are the more concrete data on the performance improvements and things like this?
So the performance for the data, we've been benchmarking with a variety of apps, DApps right now. We've worked with Binance Chain and we've gotten some benchmarks back. The reads were in the thousands of transactions per second. I don't have the numbers on me right now. But and the writes are relatively fast as well. I think the biggest thing is that the current implementation we have is in Node, and we're pushing towards a C or a Rust implementation. Okay. Urkel DB right now has an implementation in C. It just we had to add a lot of functionality to Urkel DB. So, to transform it into C, we would have to update it.
Okay.
But for Urkel DB, yeah.
Go ahead. Yeah.
No, yeah, go for it. Sorry.
No, I was just asking, like, whether you have tried it. I mean, you mentioned like Binance Chain, right? I wonder whether you have indexed something like Ethereum, the current Ethereum chain, to see how. Yeah. Yeah.
So the point of the read layer is not to index the entire blockchain. It's to create DApp specific indices.
Oh, sure, yeah.
And the reason that you want to do that is you want to, first of all, it's almost impossible to be able to index the blockchain effectively for all DApps, right? To be able to store the state for all DApps. So we don't want to have to we don't want to store all of that state. Instead, we want to store this state, and we want to be able to scale this DApp state with the usage of the DApp.
Sure. And yeah.
If you tried to index the entire blockchain, right, and you tried to serve data for a DApp, you would have to scale with the block, you'd have to scale like a full node as well.
Yeah. I mean, I think there are different approaches, but I guess I'm more interested in, like, sure, I mean, we talk about specific dApps, but I wonder whether you have like any like data on how well it's doing, and so.
Yeah. So I believe that the Urkel DB is able to do 100,000 transactions per second. You can correct me on that. It deals with batches as well. One of the concerns I get is you have to deal with the compression and snapshotting of it as well. So it's difficult to get the actual size of this state for the blockchain unless you go through all of it. Right, unless you go through every single block, because you're going to have a lot of branches that get pruned from the blockchain. If you're trying to save all versions and determine how effective it is, you need to be able to ensure that those, you need to be able to ensure they can store all the information. So it is effective. You guys can check out the GitHub. One of the things that we kind of took from this, though, is just on the lines of read optimization. If I can continue on that, on structures for read optimization, unless you have some more questions on this.
Sure. Yeah. I mean, go ahead. Yeah.
Yeah. Yeah. So the performance, I would benchmark it yourselves if I were you. The performance generally runs in the tens of thousands of transactions per second, and it remains stable as opposed to decreasing over time. So I mean, you could get significantly high transaction speeds, update speeds on a blockchain, during the interim initially, if you just use a lot of memory, but it doesn't scale at all. And that's, that's the issue that people are running into. So one of the things that we're moving towards is we want to determine how to create this read optimized data structure and what is it going to look like. And for that, we wanted a variety of different functionalities. Read optimized authenticated data structure. I'm going to call it an ADS. Authenticated data structure, you can prove that something's there. You can prove range. You can prove put, get, similar to like a Merkle tree. So what we did is we thought, okay, what are traditional databases using? Traditional, complex databases using something like SQL, Postgres. They're using B+ trees. And the benefits of B+ trees is that they allow, efficient scans, multi-range queries, multi-index queries. And they're actually, they're relatively flat because they have a high branching factor. So yeah, the way that a B+ tree is structured is it has a certain branching factor in each node. And as more values come into a node and it hits the limit on its branching factor, it actually divides these nodes and splits them. Now let's say here, right? Say 1 and 2, 1 and 2. And it splits them to balance the tree. And I think this is a more effective method than something like a rotation. But just because of the amount of usage in it, the thought was, how do we Merkleize a B+ tree, and how do we do it in as efficient a way as possible? And our solution for this was a B+ Merkleized tree, a B+ Merkle tree, which, do you guys have any questions on the B+ tree, by the way? No questions on the B+ tree? All right, well, I'll draw it out. So the easiest way to look at the B+ tree, at least for from the perspective of creating an authenticated data structure, is to look at what the individual nodes look like. So each individual node has a variable number of keys, variable number of elements in it. And these are all ordered. Initially, right, if you're trying to do something like a Merkle B+ tree, where it's similar to Patricia Merkle trie, you would get massive, proof sizes, because this variable number of elements ranges very high, right? It can be it's in the hundreds, generally speaking. So you don't want to have to hash all of these values, right? You don't want to have to hash, key 1, key 2. You don't want to have to hash all these. It's going to be expensive because you're going to have to provide as a witness all the other hash values that you need. So instead of doing that, why don't we use, we said, okay, let's try to use constant sized intranode hashes, some method for constant size intranode hashes. And then, constant size proofs, constant size intranode proofs. And if you can do that, if you can solve that problem, then you can actually solve the problem of creating an efficient B+ tree structure. What that allows you to do is it allows you to create, a higher level of queries. It allows you to use the potential for relational data, and it creates significantly more efficient proof sizes. And the way that we're able to do these constant size proofs is by using a polynomial commitment scheme.
Is this the Kate scheme?
Sorry?
Is this the Kate polynomial commitment?
Or Kate?
Yes.
Well, I don't think it's, I mean, I don't think the proper pronouncement. Okay, whatever.
What?
Don't need to.
Is it Kate?
Don't need. Yeah, I think it's Kate. Yeah.
Yeah. So
or
the
like
way
some like French or I don't know.
Yeah. So the interesting thing about polynomial commitments is that they're a very niche form of vector commitment schemes, or of order preserving commitment schemes, because they require you have to know the number of elements, right? So you know the element. In order to create these proofs, you have to know the number of elements in the proof, right? Or the data
They also
set.
require trusted setup, right?
Polynomial commitments. It's like, what is a trusted setup? Right.
Trusted setup is something that is done by something who is not you, who you need to trust.
So you have to trust some. You have to trust some individual specifically, right? You have to trust some initial hash. You have to. I mean, you have to take the generation from someone, right? So you do have a trusted setup, but you only have to do it once. And it's in the generation of the public key. So the trusted setup is yeah, it's for the creation of the public key. So it's for the creation of the initial polynomial commitment. And when I mean the initial structure of the polynomial commitment, when you're initializing it. So say I want to create a polynomial commitment scheme that will have, at most 500 elements. I would have to generate the public key that would be able to that would be able to compute to verify the witnesses for that. But I could do that before I actually create the polynomial commitment scheme, or I could reuse someone else's public key, right? Does that answer your question, Alex?
Yes. However, so are you implying that I can do trusted setup myself instead of trusting someone else's? What sort of resources will it require from me?
Yeah, so it's a trusted setup once.
Yeah, so that part I understand, but I think so like, for example, in Zcash, right, which also requires trusted setup, they have done it for us. And so today, if I use Zcash, I have to trust the trusted setup, which was done by
yes,
if I remember right, by a very small number of people. It was under 100, right?
Yeah.
So it is an extremely high level of trust, right? So to use Kate, do I have also to trust some small number of people not to commit malicious behavior at some point in the past?
You have to trust someone to generate it. Yeah. It depends on how you want to generate it. It doesn't have to be a small number of people. If it's a high number of people, though, it's going to be there's going to be a lot of difficulties in generating it. Right now,
also is trusted setup, like, do all those people need to be online simultaneously, or can they do it like iteratively?
For the trusted setup, I don't know if it matters. At least it's done once, right? So you can take a trusted setup from something like Zcash and you can use that. You're just trying to compute the base, right? You're trying to compute the base that no one knows. Yeah. But I would say that the trusted setup for these polynomial commitment schemes, I would say it's a security flaw, but it only needs to be done once ever. And I'm reasonably certain there have been other generations of it. So I think you can use security providers generation of the elliptical curve. So I don't know if it's going to be a huge issue. But it's a potential security. It is a potential security concern. I think that I don't think that that's the primary concern behind polynomial commitment schemes, though. I think the primary concern for why they're not used is because they, you're required to know the number of elements and you can't change that.
But in your particular case, is it not the case? Like in the B plus tree, you design it in a way that you know exactly the number of elements, right?
Yes. So that's when it comes in handy. But if you just, so when polynomial commitment schemes were initially created, the argument for why they had drawbacks was that you need to have the number of elements known, right? So if you want to have something with 1 million values, you need to generate a public key that's, in relation to those 1 million values. Right?
Sorry, go ahead.
You have to generate the the polynomial commitment public key for 1 million values, and that's expensive. It's a huge public key. If you're doing it for something like 100 values and you're reusing that public key for every single polynomial commitment, it shouldn't be an issue, right?
And so in your particular case, what is the size? Like what size of the B plus tree you use per node? What branching?
So right now we're still working on the B plus tree. We're still going over that. I would say that the traditional branching factors range from like around 100 to 200. I know there's some that have branching factors of like 500. You have to, you have to meter that with the size of the public key that you want everyone to share, as well as, there are reasons that there aren't, 5,000 node, 5,000 branching factor B plus trees. And that's because of the issues with sorting the keys, right? You still have to iterate through the keys and sort, when you're searching them. And maybe that's like a quick sort, you can make a fast search, but it does have diminishing returns to scale if you're going to be increasing that branching factor. So it's not an end-all solution, but it does structure this data in a way that can be used by variable branching Merkle tree. So we thought that the B plus tree was good. We wanted to use that specifically for the queries and being able to do scans and range proofs. But you could use this for an M-ary tree. You could use this for the base 16 radix. It's just a polynomial commitment scheme that allows you to create efficient constant size proofs for within a node. I don't think I would recommend doing it on something like a Patricia Merkle tree, just because I don't think it would be worth it for a branching factor of 16. But it's up to you. You could, maybe it's an interesting, maybe it's something worthwhile. Specifically with write based, I know I'm trying to talk about differences between write and read, but there is a reason for that. So specifically with write-based approaches, you don't need a high, my understanding is that you're not going to need a high level of complexity for queries. Is that, yeah, I guess what are you guys seeing with your, with the nodes when they're writing data? During consensus, are you guys, do you search through a lot of ranges of data, or how is that data being? Yeah, Alex.
Well, I don't have the actual data, but I think that
just in general, right?
As of today, I think we're mostly hitting the state size is not that large yet, but also even if the state size was large, I think that the average workload will be primarily hitting worm data. But if we were to optimize for the worst case would be hitting some random position on every write or on every read, right? So that's what like effectively the idea here is that in the blockchain, the gas price of read and write should be optimized or like computed with the case in mind that every single write goes to a random place on disk, and through the worst possible branch in the tree.
Well, it does go to a random place on disk, right? All of the nodes are going to be random. They're not, there's not going to be some form of indexing or ordering if you're just basing it off of a Merkle tree. I was more talking about when you're dealing with validating transactions in the blockchain. Do you validate these operations? You have to, you do have to get data. What type of gets is that? What type of requests and rights are you needing for that data, specifically with regard to updating the blockchain?
So those are Merkle tree reads and Merkle tree writes.
Okay, and that's what you're using? Because the point is there's different reads or nodes that are focused on consensus and writing data are going to be using that database and that data structure in a different manner than someone who is querying that, index DApp data. And so for something where you're dealing with a lot of rights, potentially a self-balanced tree might work. But maybe you want to use something like a binary tree because you don't need range queries, right? You don't need scans. You just want to do gets and puts. So it's definitely up to you. I would say if you're just looking at gets and puts, the Urkel DB might be helpful. Just because it's faster, it still doesn't allow you to, or their methodology, our methodology allows you to have kind of a variable size key, and enables you to store, actual strings as key values. So you don't have to actually hash the keys. You can store keys as bytes or strings. But yeah, I would say that the focus in a lot of these things is the data structure is definitely going to be influenced by what you want to do with it. And so this is the core thing. The flat file, if you only get a couple of things right, the flat file Merkle tree, the flat file system is the way to go for your data storage. And when dealing with consensus layer, blockchain layer, you have to optimize the index structure for that specific layer. For instance, the B+ Merkle tree, one of the aspects of it where it wouldn't be able to match other trees is you can't version it. You can version the B tree, but you can't version a B+ tree. And so you get difficulties in that if you're trying to work with that methodology. So you get the scans between nodes. Sorry, you get the scans for the B+ tree with nodes, where you can go between keys. Right, so say you have this this set of keys and values. You can scan through the entire database in a B+ tree, which is super helpful for range queries, right? So you have, but yeah, you lose the versioning. So it's all about what you want to optimize. And yeah, if you want to optimize rights, maybe go for something like an IAVL tree or a self-balanced tree, where you have some bound on the height, some deterministic bound on the height. Anyway, I think the process or the methodology of this is kind of it's what's informing the overall system, where you have the blockchain data, right? Some form of state transition. Into authenticated data, into an authenticated data structure. I think that this is the methodology that we're focusing on for the read layer, just to push information off on you guys, off of the actual full nodes. So we've been testing this with a couple of DApps. I know I mentioned that we're looking at pushing the test net out sometime in the next week, and we want to go as far into the mainnet. So we want to go into the mainnet depending on the feature set, right? We don't want to get feature bloat, but if there's a lot of features, it's going to increase the timeline. But we're looking to get that in 9 months. I think the B+ tree is going to take longer specifically, but we're hoping to have an optimized version of the Urkel DB before we go to mainnet. So taking the variable length keys and the range queries and sorts, and the range queries and the optimized range, the optimized proofs for the range queries in pushing that into C is going to be happening for mainnet as well. And yeah, so I think that's kind of describes the split between the write layer and the read layer, and how the write layer is where the consensus goes. And the read layer is where, this read layer is where we have the authenticated, we call it, Proxima DB, which is the added functionality of, the range queries, variable length keys, and, design that's focused specifically towards reads. Yeah, so I don't know if you guys have any questions, but.
I don't have any questions, and if no one else has questions, I think maybe it's a good time to end it here. It's already been more than an hour. And
Alex has got a question.
No, I was going to say that there's no questions on my.
Oh, okay, really? All right. Yeah, so this type of system where it is kind of our thought on the future of the blockchain data layer, and the flat file structures, I think, is going to be the future of authenticated data structures.
Yeah. I was thinking quite a bit on this, and we also were discussing it with the who was it from Ethereum Foundation? Dankrad?
Right? Dankrad, yeah.
Yes, and I think we sort of ended up in that state where we said, yes, it would be great to have some tree with large branching factor and Kate commitment. But I think that, like in Ethereum too, they definitely at this point not ready yet to proceed with Kate. And neither.
Yeah. Are they trying to implement it for an Ethereum, a Patricia Merkle try?
I think so. I don't think that.
I think they want to just get rid of. I don't. Yeah, I think they want to use just not use the Merkle proofs and use the Kate scheme for witness, and I'm not exactly sure how exactly they want to do it.
Do they want to use it like?
Well, I mean, the conversation happened mostly in the context of stateless validation, where we talked about
so that was
Yeah.
Okay. Well, yeah. So that's awesome. So yeah, with this type of methodology, you can scale dynamically, specifically with the DApp, instead of having to scale the complete blockchain in full nodes with the DApp. So it's it's more efficient, definitely. But yeah. Anyway, no one else has any questions. No one?
Awesome. Thank you for being here today.
Yeah, thank you.